All right, hello out there. Today we're going to be chatting about the sun's path on the celestial sphere and the shadows that get cast opposite that sun. And of course, that's what led to the sundial, right? And then eventually the modern clock, all based on the sun's position, light shines on something, and then a shadow is cast, and that shadow moves throughout the day like the hands of a clock do, and at the same rate, of course. Okay? So pretty wild stuff. Here we go. Check out this sped up footage of the sun passing over a park area, and you can see the shadows changing throughout the day. Check it out. All right, now this obviously once again sped up. The little blips of people you see, or because it's going so fast. Normally it would be at a rate of 15 degrees per hour, but you can see the shadow going around this lamppost here like the hands would move around a clock. That would be the minute hand, of course. Excuse me, that would be the hour hand. Excuse me. Pretty cool stuff, huh? All right, and here it is. Why are shadows different in length? Well, that depends on the angle that the light hits it. So if you're directly overhead, technically you have no shadow, right? If the sun is directly over your head, which in Elmont it won't be. But if it were, you would have no shadow cast in either direction. And that would happen, of course, at solar noon in the location where the sun is directly overhead. As the light gets lower, you start to create a shadow effect. And the lower the angle of light, the longer the shadow will be. Okay? A lot of photographers prefer to take pictures in the late afternoon because of this long shadow effect. Makes the pictures far more interesting. Okay, so the daily effects on shadows, check it out here, all right? Of course, they're going to be shortest when the sun is at its highest point, and that's going to be solar noon, all right? If the sun is directly overhead, again, in Elmont it won't be, but if it were, you would have no shadow, okay? The longest shadows are going to be, of course, at the beginning and the end of the day, right? Your sunrise and your sunset. And shadows will always point north at noon because the sun is in the south at noon, right? It's always going to be opposite. And that's why they say that moss will grow on the north side of a tree because the intense sun, right, the solar noon sun is coming from the south. So on the north side of the tree, it's nice and cool and shady, and that's where the moss can grow. And we mentioned this on your house as well. You notice there's one side of the house where the siding tends to get a little green and algae and moss type of growing. That's more than likely the north side of the house. Okay, this is showing you a simple little setup you can do with a pin and a piece of paper. And throughout the day, you can mark where the shadow is. And of course, you're creating your own face of a clock in a sense. Okay, the seasonal effect on shadows are similar, right? In the summer, the sun is higher, so our shadows will be shorter. And in the winter, of course, the sun is lower, so your shadows will be much longer on the average, right, throughout the day. So make sure you get that into your notes there. All right. So here we're going to try to determine the shadow's compass direction based upon where the sun is in its arc throughout the day. So we're going to be in Elmont, New York, right? This is going to be an equinox day, as you can tell, right? Rising due east and due west, all right? An equinox day in Elmont. And that, of course, is either March 21st or September 23rd, plus or minus a day. Okay? We're going to start out at sunrise, which is roughly about 7 a.m. And, of course, equinox days are 12 hours in length. So if I'm rising at 7 a.m., then I'm going to be setting at 7 p.m., right? Okay. So in this case, the sun is directly east. So when it hits the person, the shadow will go directly west. All right. As the sun rises, however, you'll notice it changes position. Now it's no longer directly east. Now it's south of east. All right. This is about an hour later, about 15 degrees worth of arc. And if the sun is now coming from the southeast and hits the person, then what way will the shadow go? Well, it's going to be opposite, right? It's always opposite where the light comes from. So if the light's coming from the southeast, the shadow will go to the northwest, all right? And there it is. You can see his shadow going toward the northwest, opposite the light coming from the southeast. You'll also notice it's a long shadow because the sun is quite low in the sky at 8 o'clock in the morning. All right, so there we keep rolling. And now we're up at solar noon, right? About 4 hours later, 15 degrees per hour. That's about 60 degrees total of arc since 8 a.m., right? There it is, about 60 degrees of arc. And now we're up at solar noon. Well, if you notice, the sun is in the south. So when it hits the person, the shadow is going to go towards the north, right? The opposite way. And it's also going to be longer or shorter, you think, than this shadow here. Hopefully you said shorter because the sun is higher. And there it is. Look at that cute little baby shadow there heading toward the north. It's a lot shorter because the sun is a lot higher in the sky. All right, let's keep rolling. And down it goes, right? That's about 3 p.m., so 15 degrees of arc. It was 3 hours, so that would be 15 times 3. That's 45 degrees of arc since solar noon. The sun moved, okay? Well, now look at the sun. And this one sometimes is tricky for students to see, but as you can see, it's in the southwest part of the diagram there, all right? Well, if the light is in the southwest, when it goes down and hits the person, the shadow is going to go the opposite way. So what's opposite of southwest? Hopefully you said northeast. Okay? And there it is, the northeast shadow. You can see it's a little bit longer than his noontime shadow because the sun is getting lower. Okay? Hopefully that makes sense to you. Now we head towards sunset in the west, right? 7 p.m. We started at 7 a.m. That's a 12-hour day, right? Equinox days are always 12 hours. And now the sun is directly west. So when it hits the person, the shadow will go directly east, and it will be very long because the sun is low in the sky. All right, I hope that made sense to you there. If you got to play that back, please do. All right, in which compass direction must the observer look to look at the noontime sun? You should never look at the sun, right? Trick question there. But it will be in the south, so you want to look towards the south. And if you were lost at, those situations, lost in the woods type of thing, well, around noontime when the sun's at its highest point, that's going to be south. So you can orient your compass based on the sun. All right? Noontime sun is always seen in the southern horizon in the northern hemisphere. Okay. Here you have Polaris over there. So please take a second, hit pause, draw in the June 21st and December 21st path on this diagram. Go ahead. All right. Hopefully you got your summer path started over here. So sunrise is north of east. Sunset is north of west. This angle, remember, would be equal to the Earth's tilt. So about 23.5 degrees higher than the equinox, right? The equinox is about 50 degrees solar noon. So that's about 73.5 right there. When you draw your lines, remember we go solid in the front, dashed in the back, gives you that 3D feel. Okay? Same thing for the winter path. Now we're starting south of east. We're going to sunset south of west. Our noon is going to be 23.5 degrees lower than the equinox, right? So 50 minus 23.5 gives you about 26.5 degrees. And you get a nice solid arc in the front, dashed in the back for that 3D effect. And when you draw them, folks, try to make them as symmetrical as possible. Make the spacing even. All right, do the best you can. I know it takes practice, but you'll get it. Okay? Okay. Label 2 p.m. on the June 21st path. So take your June 21st path and draw a little sun at 2 p.m. Hit pause and do that right now. All right, well, let's see, 2 p.m. This is the morning time, so there's no p.m. here. All a.m., a.m., a.m. Here's noon, and you have to go a little further past noon to get to 2 p.m., right? Right about in there is your 2 p.m. time. Remember, that's 15 degrees per hour, so that's about 30 degrees of total arc, right? 15 times 2. All right, if you got that in that position, nice job. If not, try it again, and if you still don't get it, please make sure you ask when we get back to the meet. How many months apart is the sun's path from December to March? Well, December to March is here. How many months is that? Well, December, January, February, March, right? There's 3 months. And then from March to June, well, that would be March, April, May, June. That's another 3 months. Well, that's only 6 months. Where are the other 6 months? Aha! The sun starts to go back, right? It's called the diurnal path of the sun. So watch carefully, folks. Here we have December to March, and of course, that's 3 months. From March to June, of course, that's 3 months. But that's only a total of 6, so you got to double back, just like this. Watch carefully. Here we have December, January, February, March, April, coming at you, May, June, and now you go backwards. Right now, the sun was at its highest point. Now it starts to get lower again and head back towards winter. So here we go. July, August, September, October, November, and of course back to December. And a lot of students don't realize that this path is going to repeat twice throughout the year, and that's why it's diurnal, right? Di meaning 2. Okay? Draw the May 21st path, hit pause. See if you can figure out how to draw the May path, right? We've been doing the solstices and equinoxes. Try to draw the May path. Hit pause. All right. Hopefully you're starting here, ending about there, right? A little before the June sunset. Hopefully your solar noon is a little below the June 21st solar noon. And again, a nice smooth arc up and a dashed one in the back. And that's what the May 21st path would look like. Okay? It's not going to be perfectly accurate, but you can get a pretty good idea there. All right. So on this diagram, I'm going to throw some things at you in the meat to try to draw in. So don't worry about this one for now, but please crank out the summary questions right now. And then we'll go through this together in the meat. See you there.